So we're starting on chapter 4 today. There was an update to the schedule, so make sure that you check the schedule for next week, midterm schedule change. So that was something that I looked at the calendar and decided that it was going to work out better that way. So next Friday, plan on a midterm, and we'll have the homework for chapter 4 due the same day as the exam, essentially. I've actually thought about doing, I'm thinking about actually making the quiz due Wednesday of next week instead, or Thursday, so that you guys will have done that before the exam day, gotten your practice in. So I might be adjusting that a little bit too.
Is next week's homework included in the midterm?
Yeah, the one that's due next week, yeah. So it'll be over chapter 4. So chapter 4 will be the last chapter we cover for the midterm exam, and yeah, nice round out our discussion of electronics by themselves, and then we're going to do a more electromechanical approach after this. Okay. So, chapter 4, nonlinear and multiport circuit elements. Thus far, we have considered only one-port linear circuit elements. One-port elements have two terminals. So, our resistors, our sources, our inductors, capacitors have all had two terminals, and so they've all been one-port elements. Linear elements have voltage-current relationships that can be described by linear, algebraic, or differential equations. So everything that we've talked about so far has had that quality. Multiport elements are those that have more than one port. I know, shocking. In this chapter, we will consider several multiport elements: transformers, which are two-port, transistors, which are also two-port, and op-amps, which are four-port. Nonlinear elements have voltage-current relationships that cannot be described by a linear algebraic or differential equation. The convenient impedance methods of chapter 3 apply only to linear circuits, unfortunately. So we must return to the differential equation-based analysis of chapter 2. In this chapter, we will consider several nonlinear circuits containing three different classes of nonlinear elements: diodes, transistors, and op-amps. Okay? So if that sounds intimidating, it's because there really is a huge amount of material that we could talk about in this. This makes up a vast amount of electronics. But we're only going to scratch the surface in this class. We're just going to try to scratch it in a way that's useful to us and gives us a start in it. So a great number of the most useful circuits today include multiport and nonlinear elements. Tasks such as AC to DC conversion, switching, amplification, and isolation require these elements. We explore only the fundamentals of each element considered and present basic analytic techniques, but further exploration is found in these references. And so I encourage you to explore them further. So I added to this, so the one that you guys may have printed out at the beginning of the term, I added that this reference here, which is a new free textbook PDF. You can get a hard copy. You can pay for a hard copy, but the PDF is free, like legally free. Yeah, unlike the other free ones that you have. Okay, so good. So any questions on like broad strokes what we're doing in this chapter? All right. Cool. So I guess I'm recording. I actually just like realized that I might not be recording. We'll see. I'll record the other one if not. No big deal. Okay. Great. Transformers. So let's just hop in. There we go. So, Lecture 4.1, Transformers. So transformers are two-port linear elements that consist of two tightly coupled coils of wire. Due to the coil's magnetic field interaction, time-varying current through one side induces a current in the other and vice versa. So let the terminals on the primary or source side have label 1, and those on the secondary or load side have label 2, as shown in figure 4.1. So this is the circuit diagram, circuit symbol for a transformer. Now, these two vertical lines there are only present when you have a core of some sort of material. So just like with a transformer, which is also a coil of wire, right? This is two coils of wire. There's a core often in a transformer as well. And the core, if there is a material core, a solid core, then we see these vertical lines. If there's not, then you see the same symbol but with no vertical lines. The so-called air core would have no vertical lines in it. So these devices are very efficient, so we often assume that there's no power loss. So it can transfer power through it without losing any power. It's a pretty good assumption most of the time. So these devices, so with this assumption, the power into the transformer must sum to 0. So in from both sides must sum to 0, giving us one voltage current relationship. So if we have the power going in port 1 on the left side, and you add it to the power going into port 2 on the right side, this has to be equal to 0. And we know that the power can be expressed in terms of the voltage and the current. So we know that V1 times I1. If we subtract the other term over, we have is equal to negative V2 I2. Note that with two ports, we need two elemental equations to fully describe the voltage-current relationship. So we have one relationship that describes the relationship between the voltage and current on one side to the voltage and current on the other side. But since there are four unknown quantities in this element now, so we've got voltage and current on both sides, we need one more equation. And the other equation can be found from the magnetic field interaction. And I'm just going to sort of skip a little bit of the physics and boil it down to the equation. So let N1 and N2 be the number of turns per coil on each side. Okay, so on one side you have N1 turns in the coil, so it loops around N1 times. And the other side, N2 turns in the coil. And we're going to define the ratio N to be N2 over N1. Then it can be shown that the voltage on side 1 divided by the voltage on side 2 is equal to 1 over N. These two equations, so 1 and 2, can be combined to form the following elemental equations. So if you take those two and do a little bit of manipulation to them, this second one very clearly gives you this first equation here. The other one can also be shown to be true using the second one in the first one. So we have a relationship between the voltage on one side and the voltage on the other side, and a relationship between the current on one side and current on the other side. Okay, so these two equations are the elemental equations for a transformer. So just like when you had an inductor, you had a relationship between the voltage and the current for it. For a transformer, we have two equations that we write down. And they're actually conveniently algebraic. There's no differential equation here, which is nice, right? We like that. Great. So we can step down voltage if n is less than 1. So the voltage on side 1 gets multiplied by something that's less than 1, and we get out a voltage that's lower, right? This is better in some cases than the voltage divider because it does not dissipate much energy, which is nice. However, transformers can be bulkier and somewhat nonlinear, so it's not always the best choice. And then this is another reason why it's not always the best choice. They only work for AC signals. So they only work for sinusoidal signals, and they will not work for a DC signal. So you can't step down, you can't use a transformer at all for anything useful for a DC signal. It essentially just doesn't transmit anything through it. So it's kind of disappointing, but it's the sad truth. Okay. Note that when we step down voltage, we step up current due to our power conservation assumption. So if we step down, so if n is less than 1, we step down the voltage, then this ratio is greater than 1, and we step up the current because power is conserved. So it's good to keep that in mind. Okay. Alternatively, if n is greater than 1, we can step up the voltage. Okay, so that's new. Voltage dividers couldn't do that for us, right? Voltage dividers could take a fraction of the input voltage and give us an output voltage, but they couldn't give us an increase in the voltage. It is not amplification, however, and this is important, because power is conserved. So we're simultaneously stepping down the current. So we step up the voltage and down the current. So with the transformer, we can freely trade AC voltage and current. So that's what we can do with the transformer. So that's why on our power lines, we have transformers throughout, and that's what that's doing is that's trading. It's trading voltage and current for us. Okay, and all of our power transmission lines are AC. So we can use transformers to do that. Relatively lossless, but there's going to be a little bit of heating that happens, and that's lost power. So they're not perfect. They do lose a little bit each time they're transformed. So let's do an example, shall we? Okay. Given the circuit shown, and this changed slightly from the one, so unless you printed it out last night, it's stated, I think it's stated more clearly in the way that I've stated it here. So in your notes, if you printed it out previously, please try to make sure that you recognize the difference here in the way that it's stated. The circuit's exactly the same, and actually the problem is the same, but it's just stated more clearly, I think. So given the circuit shown, what is the effective impedance on the ZL, or of ZL on the source side? So we have a load impedance. I didn't define what kind of element it is. It's just some load impedance, ZL. And we want to know what its effect is on the source side of the circuit. So we imagine that we're supplying some voltage here, and the two sides of this transformer, they transmit this voltage across, supplied to the load, but the load is also felt by the source circuit, right? The source circuit gets loaded by this load circuit, but it's loaded through this transformer. So we want to know, how does this load affect the source when it goes through a transformer? And this is kind of a common situation. So we want to become comfortable with it. And this is actually a result that we can reuse once we derive it in this problem. So we'll go through it. So we're talking about impedances. We could, so remember, I said at the beginning, impedances don't work for nonlinear circuits. Is this a nonlinear element? Is the transformer nonlinear? No, it's linear, right? It's linear because the elemental equations are linear equations. They're actually algebraic too. But since they're linear, all of our impedance methods still work for transformer circuits, okay? So I said, impedance is out, but the one new element we're going to consider this chapter that's linear is the transformer. So we still can use impedance for transformer circuits, and that's what we're doing here. When you get to the rest of the chapter, we're going to be doing nonlinear circuits, and we can't use impedance anymore. But for this stuff, we can still use impedance or differential equation methods. So chapter 2 or chapter 3 methods still apply to transformer circuits. Okay, so we've got our circuit. We can use our chapter 3 methods of analysis. So we could, I'm actually going to try to lead us, we're interested in something really specific in this problem. So we could use our whole chapter 3 methods, and we could find all of the unknown voltage and currents, right? But in this problem, we're just asking, what is the effect of the impedance ZL on the source side? So what we really want to know is, what is the impedance, the effective impedance of ZL in the element 1 position in this circuit? Okay, how does, so we might restate this. How does, or maybe I'll say what? What impedance does element 1, it's not a real element, right? But the one side of the transformer, element 1, have on for the source, because the source is looking at the one side of the transformer, right? So we might just start with writing what Z1 is. So by definition, we know that Z1 is equal to V1 over I1, right? That's the definition of the impedance. So on the one side of the transformer, it has a voltage and it has a current. So the effective impedance of that side is V1 over I1, okay? And so our goal then is to rewrite this in terms of ZL. That's what we want. We want to rewrite the voltage and the current in terms of ZL. once we've done that, then we're going to have our relationship that we're interested in. How does ZL affect Z1, essentially? So we could apply the transformer elemental equations So I'll rewrite Z1 equals, V1 is V2 over N, right? And I1 is negative N times I2, right? So V1 becomes V2 over N, and I1 becomes negative N I2, right? So if we simplified this, the n's can combine, and we get negative 1 over n squared times V2 over I2. So now let's look at, so this right side, now we're on the, so in V2 and I2, we're on the load side of the circuit. We're trying to make our way over to ZL, right? So if we could write voltage 2 and current 2 in terms of voltage L and current L, then we might be able to do that last step, right? So our, whoops, I don't know what I just did, but guess it's fine. Let's use KVL and KCL to rewrite in terms of VL and IL. So we know that. So let's do a quick KCL. So we've got IL going in here, plus to minus, so this one's going out. So we know that IL equals I2, right? So our I2 equals IL. If we do a quick KVL, then we see that this is going the other way, right? So V2 equals negative VL. Or you could say V2 plus VL equals 0, which implies that V2 equals negative VL. So therefore, going back to our Z1 equation, Z1 equals, still have the negative 1 over n squared times, now we're going to have V2, negative V2, and, negative VL and IL. Or just 1 over n squared times VL over IL. Sweet. Now we've got we have a desire to write it in terms of ZL. We have a fraction ZL or VL over IL, right? What is that by definition? ZL. By definition, right? VL over IL equals ZL. So we have that Z1 equals 1 over n squared ZL. So this is a really useful result. If you're going to use impedance methods to do a circuit analysis with a transformer in it, then what you can do is find the equivalent impedance on the load side. So you can combine, so this didn't have to just be a single load. It could have been a bunch of impedances, right? And we could have combined them all down to an equivalent load impedance. And then instead of having to go through this whole song and dance, we can just say, oh, it reflects through the transformer and has an effective impedance on the other side that is the load impedance divided by n squared. So that's kind of nice. It's kind of like, I mean, you can think of this as being the sort of impedance equation for a transformer. Okay, the impedance on one side is reflected through using this relationship. Okay, and transformers have that nice use that we use them for. They're power transmission. We already discussed a little bit about, and they're really useful. But the one thing that is sort of a detriment for us with using them is that they tend to be bulky. And like the transformers are like the big things you can see out there on the power lines. So they tend to be big, beefy things, and they're often expensive. So that's one, and they're also often heavy. So they take up a lot of space. When you're designing a small product or a small machine, and it needs to be like maybe small and lightweight, putting transformers on is not usually your friend, but still really useful. And in certain applications, maybe most applications where you're going to use one, you're going to be stationary. It's going to be hooked into the grid, and you're going to be transforming the power coming from the grid. Maybe you have to run a motor that would be better off with a different voltage than what comes off the line. So you use a transformer to give yourself a different voltage. And it can also be used to isolate one circuit from another circuit in terms of the DC component, because the DC part is completely ignored by the transformer, right? So you could have two circuits with completely different DC components, so there could be a different ground even. But they'll transform the AC part just fine through them. So they can kind of interact in an isolated way. So they're useful for that as well. So lots of applications. You see them come up a lot. But now we can deal with them, using impedance methods, but also using differential equation methods as well. There's no reason why we couldn't use these same transformer elemental equations in our typical circuit analysis techniques of Chapter 2 as well. So, yeah. All right, any questions on transformers?